Between the Earth and the Moon, there are places people almost never imagine. They're not points on a map, not orbits by eye. They're points of equilibrium, where two forces of attraction seem to hold an object in place. You can't see them in the sky, but half of the lunar logistics depend on them. Relays, navigation, future stations, communication windows, and the scariest thing is, they look like a guarantee. We call them Lagrange points, but don't get hung up on the term. Imagine a saddle on a mountain. In one direction you seem to be in equilibrium, but if you push, you're blown off course. That's why the devices stand there. They're not fixed in place. They balance and constantly adjust their steering, but the adjustments are small, as predictable as breathing. And it was this breathing that broke down first. Not an explosion, not an engine failure. It was just that the fuel consumption was slightly higher than normal. It was too smooth, too consistent, to be attributed to chance. At first, it seemed like nonsense. One device was making an extra correction pulse, then a second, then a third, and all in the same time frame, as if someone had shifted the floor beneath their feet. You've heard about 3i Atlas and everyone's looking at the trajectory, the tail, what is it? But right now, someone at JPL isn't looking at the object. They're looking at dots that shouldn't be moving. Because the equilibrium point doesn't live. It's calculated from masses and distances. The Earth, the Moon, and that's it. You can calculate it on a napkin and it'll be there tomorrow. So when the spacecraft start losing position, the initial reaction is always the same. It's our fault. Model error, timing error, measurement error, command chain error. And they begin to clean out everything earthly. They check their watches. They verify the rangefinder. They recalculate the ephemerids. They recheck the light pressure. That very gentle push of photons. Nothing adds up. Because the error doesn't behave like an error. It behaves like an external influence that turns on and off according to a schedule. This is the moment when history ceases to be boring engineering. When someone sees a repeat in the log, not approximately, exactly, with the same step. The shift is small. At first it's tens of meters. For space, that's dust. But for equilibrium, it's like moving a table leg. The table is still standing, but you can already feel it leaning. Then hundreds of meters, then kilometers. And the most disconcerting thing, the devices aren't going somewhere. They're going the same way, along the same axis, as if the equilibrium point isn't blurring, but shifting. And that's when you understand why it's called a silent event. Nothing burns, nothing crashes. The entire system simply begins to use up resources faster than expected. On normal days, a device in this position has a budget. So much fuel for a year, so much for 5 years. Everything is scheduled, but then the budget starts melting like ice under a lamp. And no one can go to a press conference and say, our math points are moving, because it sounds like nonsense until you see the graphs. Everything looks worse on graphs than in words. The line should be smooth, instead it becomes jagged, as if someone is pushing the system with short pulses. And these pulses coincide in time with what's already been glimpsed in other data. Windows where 3i Atlas seems to pulsate across dimensions even though there's nothing there to pulse. From this point on, you have two options, and both are unpleasant. Either we don't understand what the object is doing, or we don't understand what equilibrium is when something untextbook passes by. The simplest picture goes like this. Equilibrium points aren't a pin in space. They're an area where forces almost cancel each other out. Almost. And almost is a door. If you add even the slightest extra force to the system, the point moves further than you expect. Because you're not pushing a rock, you're pushing a balance. That's how a saddle works. You can stand on it and feel stable. But if a crosswind blows for a second, you're already sliding down one of the slopes. And this is what the devices see. It's as if they've been caught in a crosswind that turns on briefly, then disappears, then returns during the next cycle. And the wind isn't chaotic, it's always from one direction. It doesn't make noise. It presses just enough to throw you off balance, but not so much that everything falls apart at once. At this point, you want to ask, how can one even notice a shift in a point if it's not material? The answer is simple and cold. By how the apparatuses stop matching the calculation. They have radio communication, they have a rangefinder. The Earth senses their distance based on the signal's timing, and when the distance starts to deviate, you see it without any mysticism. Moreover, you see the direction. A measurement error creates confusion, and that creates an arrow that points neither to the Earth nor to the Moon, but in the direction the object passed. And then the tone of the conversation begins to change, because 3i Atlas used to be a topic for amateurs. Now it's becoming a timestamp in the journals of serious projects. They take one specific pulse, one specific interval, and look at what the devices were doing at that moment, and they see a consistent surge in the need for correction. It looks as if the center of equilibrium has shifted, and the devices, by inertia, continued to move around the old center until they realized that the center was no longer there. It sounds mild, but the consequences are severe. because the devices in these positions maintain contact with distant missions, with long-range lunar communications, with lines that can't simply be switched. If a repeater goes away, you don't get a beautiful flickering picture. You lose your connection window, minutes turn into hours, sometimes into days. And all this doesn't happen all at once. It happens in waves. Window after window, you begin to live according to a schedule that no one set. At first, it seems like these are just unnecessary adjustments. Then it becomes clear that the adjustments aren't keeping up, because the balance point is also breathing, and it's not breathing as it used to. It doesn't return to its previous position completely. Each cycle leaves a small residue, as if the system is being shifted slightly into a new form. And here comes a word engineers don't like: accumulation. When errors don't just disappear, but accumulate, any budget eventually runs out. You can endure a week of weirdness. You can endure a month. But when weirdness becomes a new background, you stop being an observer and become a participant. At this time, everything is outwardly calm. No news, no alarming headlines. Simply, a line appears in classified reports, increasing orbit maintenance frequency. The problem is that maintaining orbit there isn't just a matter of a little steer, it's a delicate game. You can't give it too much thrust or you'll fly off toward the moon. And you can't give it too weak, otherwise you'll be carried away to where the connection becomes poor, or where there will be long shadows, or where the temperature will start to fluctuate. Therefore, every unnecessary adjustment is a risk disguised as routine, especially if it occurs on a timer, rather than as required by the environment. Then something happens that seems trivial but is nerve-wracking for everyone. One device makes a correction at the precise moment when, according to the plan, it should have been silent. Not because he'd gone mad, because the algorithm saw the threat of escape. It saw the balance slipping out from under him. And this becomes evidence that can't be swept away, because automated algorithms don't believe in news, they believe in dynamics. After this, they begin to take a broader view. If the points between the Earth and the Moon shift, what happens to the other pockets of equilibrium in the system? There are points that are not between the Earth and the Moon, but on either side, like two anchors in the Moon's orbit. They are usually considered convenient because they make it easier to maintain position. And suddenly, even they begin to demand unnecessary adjustments. Not as much, but at the same rate. It's as if the entire Earth-Moon system has become slightly skewed. At this point, you understand why this isn't just another oddity. It affects the map of space we navigate around the Moon. We're used to thinking of the space around the Earth as a city with streets. There are intersections, there are advantageous spots, there are trajectories that are convenient for saving fuel. And now one of the intersections suddenly starts to creep away. And it doesn't creep away randomly, but in a repeating pattern. The most annoying thing about this pattern is that it's predictable. And when you predict and then see confirmation, you stop being a skeptic. You begin to anticipate the next blow, even if it's quiet. Because in space, quiet blows are more dangerous than loud ones. Loud ones immediately break everything and end. Quiet ones drag on. Here's where the next detail comes in. The shift isn't the same size in each window, but it's the same shape. Always a sharp entry, always a short plateau, always an exit, and a small residue that never returns to zero. It doesn't look like solar radiation pressure. It doesn't look like an atmosphere, because there's no atmosphere there. It doesn't look like a model error, because models are often wrong. It's like an external acceleration boost, arriving as momentum. Moreover, momentum is associated with something moving along its trajectory. And so the name 3i Atlas comes up again, as if being dragged by the sleeve back into the frame. Now you want to know the main thing, how dangerous is it? And the answer is unpleasantly adult. Dangerous not in the we're all going to die way, dangerous in the we're losing our margin of safety way. If the equilibrium point shifts by kilometers, that doesn't mean the spacecraft immediately fall. It means they must constantly catch up with what was once a fixed reference point. But fuel is finite, thermal conditions are finite, the lifespan of jet systems is finite, and most importantly, human time is finite. Because every new window forces teams to recalculate plans, change communication schedules, reschedule experiments, rebuild trajectories. You don't see it in videos about space, but it's precisely from these quiet transitions that real failures arise. And then comes a zone where there's still little data, but the picture is already forming itself. If equilibrium can be shifted by impulses, then impulses can be tuned. I'm not saying who or why, I'm saying what it looks like. It looks like the system is trying out different amplitudes and seeing where the devices start to lose their grip. Because in one window, the shift is small and the devices barely notice. In the next, it's larger and the corrections become more frequent. In the third, the shift is such that one device enters a zone where the connection deteriorates. It feels like a test of tolerance, not a random annoyance, and that's precisely what makes people stop joking. They're starting to compare not only lunar probes but also laser measurements of the Earth-Moon distance, those same ultra-precise measurements that have proven consistent for years. And suddenly a microscopic step appears in these measurements in the same windows, not huge but repeatable. It's important to understand the scale here. The moon isn't flying away. No Hollywood scene here, but if a step appears in the dimensions, it means the geometry of the force field is changing. Not at the level of sensations, at the level of the distance you measure with light, and this is too serious to be attributed to noise. Then someone asks the simplest question: if the equilibrium points shift, where do they shift relative to the moon? The answer comes from the actual vectors. The shift occurs along a line that doesn't coincide with the normal perturbations of the Earth-Moon system. It looks like an addition from the side, as if a third hand takes the system for a second and tightens it. This is what's most frightening, because the third hand in the classic painting is a third massive object or something that acts as a force. And 3i Atlas in this story doesn't need to be as massive as a planet to have an effect on equilibrium. It only needs a small boost at the right moment. Equilibrium is an amplifier. You press a button and the button rearranges the picture. It's like a tuned string. You don't have to hit it with a hammer. You just have to hit the frequency, and the string will vibrate on its own. And when you see the windows repeating, you start thinking not about strength. You start thinking about frequency. Because frequency is what connects reverse aurora, silent break, and now point shift. Different phenomena, but the same rhythm. And this is where things get tricky. Because if you have one rhythm, then you have one source of schedule. The word synchronization appears within teams. No one wants to write it in the report, but it's there in the discussions. Synchronization means that the effects don't just coincide in time. They seem to be perfectly timed. You may not believe in the alignment, but you can't ignore the fact that lunar probes begin to lose position precisely during those windows when external data provides a boost again. Now add the human side. There, at the balance points, new objects are planned. Platforms, nodes, places where it's convenient to maintain connection and energy. If these sites become alive, the entire architecture of future missions becomes more expensive and complex. And this isn't fantasy, it's budget math. You start budgeting more fuel. You start building a system with a larger margin for adjustment. And stock is mass. Mass is money. Money is time. And you lose momentum precisely when the external factor continues to move at its own pace. And all this before anyone asks the question that comes last but cuts deepest. If the equilibrium points between the Earth and the Moon can be shifted by impulses, then what happens to the equilibrium points in other systems? Not in deep space. Here, inside our infrastructure, inside the navigational nodes that determine our routes. And then the picture expands, because Earth-Moon is the closest test, the most sensitive, the most observable. If the system responds here, then we can look for similar traces elsewhere. Where is there a balance? Where is a saddle? Where a small push produces a big shift. And at this point, it becomes clear to you why the information is not coming out quickly. Because it's not a single object that can be shown in a photograph. It's an effect that you can only prove through a series of measurements, and a series of measurements takes time. And time works against us in this story, because every cycle leaves a residue. The remainder means that the equilibrium isn't simply shaky. It's being reprogrammed into a new state, little by little, step by step. And every step forces the devices to spend more than they should. This means that any mission at these positions gains an invisible timer, not a until disaster timer, a until premature aging timer. And this is the part that the viewer usually doesn't realize. In space, there are rarely moments of it's broken. More often, there are moments of it's worn out before. You want to see drama? Here's drama. A device that was supposed to last 5 years starts losing power in its third. Not because of human error, but because the space underneath it is no longer the same. Then comes night. When one of the devices fails to catch up with the point, it doesn't fall, it drifts away. Going to the side there means that he enters a trajectory where the lighting changes, where he is more often in the shadow, where the batteries work differently. The thermal regime begins to fluctuate, and every temperature spike is another hidden crack in the lifespan. The team catches the craft and returns it, but the return costs fuel, and so you're in a vicious cycle. You're wasting resources to stay in a place that no longer keeps you for free. And then something happens that makes the story truly cold. In one window, the devices don't just disappear. They disappear simultaneously and uniformly, as if someone had moved the very center of the system. It looks like a collective collapse, not the failure of one individual, but a general drift that demonstrates it's not the apparatus, it's the environment. And when the environment changes, you can no longer fix it with your team. You can only adapt and see how much time you have left until equilibrium takes a step again. From this point on, a new habit emerges. For every 3i Atlas pulse, they begin to make a forecast in advance of where the dots will be in the coming minutes. It sounds absurd, but it becomes part of the plan, like a weather forecast, only for mathematics. And the forecasts are starting to hit. Not perfectly, but enough to make the very possibility scary. Because if you can say in advance that the equilibrium point will move at 214 and return at 219, then this means that the system behaves like a repeatable mechanism. And then you catch yourself with a different feeling. We're used to the idea of space being indifferent, but here, that indifference disappears. There is a feeling that the environment is responding, not with emotions, with geometry. The darkest part of this story is that it doesn't require gigantic forces, it requires a precise hit. And precision is what always distinguishes randomness from regularity. I won't promise an apocalypse. This isn't a story about it will strike an end. This is a story about the map is quietly changing, and the map is what keeps us in space. You can live when storms are rare. You can live when orbits are predictable. But when the strange becomes predictable, that means the strange becomes the norm. And here's the final twist of the first big part, the one after which people begin to look at the moon differently. One of the spacecraft, held at the equilibrium point, records more than just a departure. It records the moment when its orientation system loses the sky for a few seconds. The stars on the sensor don't disappear, they seem to shift, not chaotically, shifting, as if the background itself had momentarily rotated. And this happens at the same second when the graph of the shift of the equilibrium point makes a step. This means that we're not only observing a change in the spacecraft's trajectory, we're also observing a change in how space appears to the instrument. Not in a philosophical sense, in a measurable one, in an ironclad sense. And when this is recorded, it becomes clear that the story with equilibrium points is not an isolated episode. It is part of the same pattern which repeats itself, grows, and each week takes away from us a little more confidence that balance still belongs only to the Earth and the Moon. And then comes the worst part. Because if equilibrium can be shifted, it can be shifted so much that the devices can no longer be maintained even with active corrections. The next window doesn't arrive like a surprise. It arrives like a bill you knew was coming and still hoped it would be late. You see the drift start before the timestamp, not because the push starts early, but because the balance is already tense, like a tightrope that remembers the last shove. The control software reacts faster, and that's your first warning. When code starts overcorrecting, it's not panicking, it's admitting the old margins are gone. At L1, the keep it there burns come closer together until they stop feeling like maintenance and start feeling like a heartbeat you can't slow down. At L2, it's worse because the shadow geometry punishes you. One bad excursion and the temperature swing climbs, and every swing makes pointing noisier. Then the points begin to wobble. Not drift in one direction, but wobble around a new center, like someone is shaking the saddle instead of nudging it. The wobble has a period, and the period matches the pulse windows that keep showing up in other data, like the system is being tapped in time. This is where people stop blaming bad measurements, because you can't fake a clean wobble across multiple spacecraft with different sensors. You measure it two ways. You measure where the spacecraft is, and you measure where the balance point should be, and the gap between them starts breathing. Breathing means the target is no longer a fixed spot. It's a moving spot that returns close, then overshoots, then returns again. The first overshoot trips an alert. The correction flips direction without a cause in the model. It's like the math suddenly changed its mind. That flip is what you feel in your stomach. Random noise doesn't flip cleanly, a driven system flips when the driver crosses a threshold. So inside JPL, they go to the one thing that doesn't care about opinions, light time. Across NASA, the language in the thread changes. Fewer jokes, fewer screenshots, more short sentences. Laser pulses to the moon, radio timing to the craft. The numbers confirm the same story, over and over. The leftover error steps, holds, and steps back on schedule. And now you have a new problem. If these points wobble, the cheap routes between Earth and the moon stop being cheap. Those routes rely on gentle dynamics, on letting gravity do work for you. When the gravity landscape ripples, the route becomes a moving staircase. In practical terms, every transfer needs extra cleanup. Extra cleanup means extra propellant. Extra propellant means fewer missions, fewer chances. That's when someone says the quiet line out loud. If this continues, L1 and L2 become unreliable infrastructure. Unreliable infrastructure between Earth and Moon is like unreliable bridges in a city. You can still move, but every trip costs more, and the risk creeps up. The next window hits, and one platform misses its planned burn by seconds. Not a mistake. The onboard logic delays because the star tracker can't settle. The star tracker can't settle because the apparent sky shifts just enough to confuse a sensor, built for clean geometry, right when the wobble peaks. So the craft burns late, and late burns at a saddle are expensive. It doesn't fall, but it slides into a path that eats battery margin. Battery margin is the hidden timer nobody wants to talk about. When the margin drops, the mission starts trading science for survival. Now the teams try to build a new normal. They estimate a moving target and design corrections around it like sailing with a drifting buoy. For a few cycles it works, and that's almost worse, because success tells you the phenomenon is stable enough to plan around. Then the wobble changes shape again. It becomes lopsided, like one half of the swing is being clipped. Clipped swings are a signature. They happen when something hits a boundary, when the system can't respond smoothly anymore. And that's when the first craft reports a mode it was never meant to use here. Fuel saver logic at a location that was chosen to save fuel. You don't need a conspiracy to feel the irony. This spot was supposed to be calm. Now it's the place that drains you. The logs show the same brutal math. If windows keep coming, the keep at their budget is cut in half, then cut again. Not because the craft is broken. Because the map it's trying to hold on to is moving under its feet. And here's the part that makes the room go quiet. The wobbles phase begins to drift, slowly, like the driver is walking through rhythms. When a driver walks through rhythms, it's searching for resonance. Nature can do that, but not with such clean, repeatable steps. The step lands right as 3i. Atlas crosses an alignment that only orbit people care about, the line between Earth and the Moon. Alignment shouldn't matter to a passive rock, yet in the data, alignment marks the moment the wobble's size jumps. The jump is small in kilometers, but huge in cost. Because at a saddle, a kilometer can be the difference between hold and chase. And once you are chasing, you never stop chasing. Every correction is a promise you'll need another correction after it. So the question changes. It stops being what is the object. It becomes what does it couple to and why here. If the coupling is gravity, it's too clean for the mass you'd expect. If it's magnetic, it's too deep for the distances involved. So you end up staring at the last category everyone hates. A tiny term in the math we don't use much in this regime. Call it a ripple, call it a twist, call it a bias in the field. The effect is the same. Balance points act like they're being redefined. And if balance points can be redefined, then the safe lanes around the moon are no longer fixed lanes. They're negotiable lanes. Stay with me, because the next window is where one platform fires a correction and discovers the correction doesn't take. It burns, it should settle, and instead the error grows. That's when you realize the target moved during the burn. That's the moment the word slip appears, not drift. Slip like a clutch losing grip. And once the system starts slipping, you're not watching a wobble anymore. You're watching a transition. You call it slippage, and the word sticks because it's human. It's about a mechanism that's still working, but no longer holding its grip, and you feel it before you see it in the numbers. The next impulse comes quietly, and this time the device does everything correctly. It makes a correction, he should return to the usual corridor, and for a second it seems like everything is fine. And then the error grows again. Not suddenly, but steadily, like the water level rising in a closed room, and you realize it's not the device that's at fault, but the point it's chasing. The worst thing about chasing balance is that you can't catch up to it once and then calm down. If the target moves away during your maneuver, you'll always be late. And that's when operators do something they hate for the first time. They start cutting tasks to save the life of the machine. Not because it's panic, but because it's math. If you spend fuel fighting a creeping point, you have less fuel for orientation, for communication, for warmth, for everything. As a viewer, you usually expect drama in the form of engine failure. But the drama here is different. The drama is that the engine keeps running, but the world it was designed for ceases to be the same. In the next window, the drop becomes noticeable even on the connection. The signal doesn't disappear, it becomes fragile as if the line is hanging by a thin thread and trembling. Short freezes appear that can't be explained by weather or ground stations. Everything is clear and the message in the log is the same. The quality drops exactly according to the timer. And this forces people to look beyond the fuel. They begin to look at geometry, at how the communication beam passes through space, which suddenly behaves not like a void. The simplest explanation sounds almost boring. If the balance of power has changed, the trajectories that are convenient for maintaining position have also changed, and therefore the orientation of the spacecraft has also changed. But the boring explanation breaks down on one detail. The apparatus begins to see not one center, but two almost identical solutions, as if the equilibrium had been split in two. Not forever, for minutes, for one cycle. And it's precisely during these minutes that his automation fluctuates, choosing which center to consider the real one. If you've ever seen your car's GPS veer between two parallel roads, you'll understand the feeling. Only here, the cost of a mistake isn't a turn, but a trip that takes kilometers. At first, they think it's a filter glitch. Then they check it with another device in a different position and see the same choice, the same question in the data. Two centers, one slightly closer to Earth, the other slightly closer to the moon. And both look plausible enough that the automation will have to decide, rather than simply follow. And here for the first time you hear talk about how equilibrium has become not a point, but an area with an edge, as if a fold had appeared in the gravitational landscape. A fold is more dangerous than a shift. A shift can be predicted and compensated for. A fold means that a small deviation suddenly turns into a large deviation. The next window arrives, and one device hits exactly this crease. It makes a correction, and instead of returning smoothly, it moves to the side faster than it should. It's like losing traction on wet pavement. You turn the steering wheel, but the car keeps sliding because the surface beneath you is different. The team catches it with a second impulse and catches it almost at the last moment, because further on begins a zone where the shadows are longer and the heat escapes faster. And at that moment, no one says, "We're in danger," but everyone understands that they've just paid too high a price for a small fix. As the price rises, restrictions emerge. They begin to preemptively disable certain modes of the device, so as not to waste resources on micro jitters and unnecessary adjustments. But prohibitions don't solve the problem, they simply make the apparatus less flexible. And a less flexible apparatus is less able to cope with a world that has become more fluid. Now watch what happens next. The pulse windows start to shift. Not much, but enough to make the coincidences even more unpleasant. Before, you could say, the effect turned on, the effect turned off. Now it starts before the window and ends after, as if the system is no longer waiting for a signal but is living on residual voltage. It's as if you were pushing a swing and then the swing continued on its own, and each subsequent push only adjusted it to a new amplitude. And this is where the real cold comes in. Because if the system has entered self-sustaining mode, it doesn't need constant stimulation, it only needs a rhythm to intensify. During one of the cycles, something happens that usually never happens. The team plans a support maneuver, and the spacecraft refuses to execute it, not because of a malfunction, but because the sensors detect the maneuver as dangerous. It's dangerous because the center is changing too quickly, and a maneuver could take it in the wrong direction. That is, for the first time, the spacecraft is acknowledging that the environment has become unpredictable on a minute-by-minute basis. And if at the minute level the points that were considered the most predictable are unpredictable, this isn't a local oddity, it's a change in the rules of the game near the moon. During this period, small things begin to happen that engineers usually brush off, but here they add up to a chain. Gyroscope noise increases slightly, the device corrects its orientation slightly more frequently. It loses perfect starlock slightly more frequently. Each little bit individually is nothing, but together it appears as a tremor in the space around a previously smooth node, and then comes the simplest and most devastating confirmation. On the same window, devices in different positions produce the same signal propagation time error. The same, in the same second. This means the problem isn't within the device. The problem lies in the signal path, in the geometry between them and the Earth. And if the signal's geometry changes according to the timer, it means that not only are your equilibrium points shifting, the way space conducts information is changing. It sounds scary, but you can imagine it simply. It's as if a lens appears in the air for a moment, and the rays of light don't go as they should. The lens doesn't have to be glass. It can be any area that causes the waves to behave differently, and you see this as a delay. This delay is small, fractions of a second. But over the distances of space, fractions of a second turn into kilometers if you're trying to maintain your balance. And that's why everything becomes an avalanche. The device calculates its position based on signals, the signals produce a small systematic error, and the device begins to correct itself for the error. That is, he spends fuel not on reality, but on a distorted mirror of reality, and the mirror turns on precisely on a timer. The next cycle brings another event that's difficult to explain as normal. Both devices simultaneously report a brief lapse in orientation. It's not a malfunction, their systems just say for a few seconds, "I'm not sure where I am relative to the stars." Then confidence returns. It's as if someone momentarily shifted the background. It's not the stars that have moved, it's the image the instrument sees that has moved as if it's been nudged. And it's precisely in these seconds that their trajectories take the most unpleasant microstep. Not a jerk, a step, as if the system had been reset to a different level. Now you understand why the word layer comes to mind, even if no one wants to say it. Because a step feels like a transition across an invisible boundary. The border isn't on a map, but in space. You pass through it, and everything changes slightly and then back again, and again, slightly different. And when this happens again, you begin to expect that at some point the transition will not be there and not back, but further. At this time, everything outside looks calm. The moon is just like the moon. The sky is just like the sky. Only inside the schedules a new column appears, which is not shown to anyone else. Risk windows. Windows when it's best not to make critical maneuvers. Windows when it's best not to conduct sensitive measurements. Windows when it's best to simply wait it out. Waiting it out in space sounds ridiculous because space shouldn't make you wait. But here it does, and it does so steadily that it almost feels like a routine. The next step is both logical and terrifying. They try to catch a new equilibrium as if accepting that the old one is dead. This means rebuilding the holding orbit, changing the amplitude, changing the phase, doing a new little dance around a new point. And for the first day, it seems like it worked. The error rate is smaller, adjustments are less frequent. Everyone breathes a sigh of relief as if they found a way around it. And then a window comes, and the new equilibrium leaves too. and it leaves as if it were seen and touched, as if it weren't a random field, but an object that could be deliberately displaced. It's that moment when you have one simple question left in your head that's too dangerous to ask out loud. If the equilibrium can be shifted, then one can choose where to move it. And if one can choose, then one can force devices into zones where they begin to lose resources faster. I'm not saying it's a goal. I'm saying it's an opportunity that suddenly becomes physical, measurable, and can't be dismissed. And then a new line appears in the data, which at first glance sounds harmless, but in fact changes everything. In the impulse window, a brief shift in the position of the system's center of mass relative to the forecast is observed. The translation into human language is simple. For a few seconds, the Earth-Moon system behaves as if it were held by more than just the Earth and the Moon. And if this is true even for a few seconds, then the next part of the story will no longer be about devices that waste fuel. It will be about how the third hand doesn't just touch balance, it begins to change the rules of gravity at the node we thought was the most reliable. And the next impulse is precisely the one where the double center becomes not 2, but 3. The 3 centers look like a mistake until you see that they aren't arranged chaotically. They appear in the same order, like 3 steps up a staircase, and each step takes the same amount of time, as if someone were measuring the system not by meters but by rhythm. The first center behaves as before. It's close to its usual equilibrium, and the apparatus can still dance around it. The second center is displaced, and the pull toward it is stronger, as toward a deeper depression in an invisible relief. And the third center is the strangest, because it's not stronger, it's simply different. It seems to appear where it shouldn't be at all, and disappears as cleanly as a light turning on a timer. If you're looking for a simple explanation, it initially seems ridiculous. It's as if the space between the Earth and the Moon becomes 3-layered for a second, and each layer offers its own equilibrium, like 3 paths on the same bridge. But then the humor dies, because the devices don't react to abstractions. They respond with fuel consumption, temperature, antenna angle, real numbers that don't understand metaphors. In the next window, the team does what they always do when they don't trust reality. They try to catch it through control. They plan a maneuver to pass through the area where the third center should appear and observe how the spacecraft behaves. It's a risky trick, but it yields a better answer than 1,000 discussions. If the third center is not real, the device will behave as usual with a little noise. If it is real, the device will begin to choose. And he chooses. The worst part is that it's not a human choosing. It's the automatic system choosing, because it sees the gradient, sees where the pull is, and does what it was taught: maintain balance. When the third center appears, the device seems to fall into a new corridor. Not abruptly, without a jerk, but too quickly for natural drift. The positional error begins to grow in one direction, and the corrections become so frequent that they sound like a nervous tick. And then, for the first time, a figure appears that makes people's fingers go cold. The forecast for the remaining fuel to maintain position is suddenly recalculated and drops, as if years had been stolen from the spacecraft. It's important to understand why this is more frightening than any pretty anomaly in a picture. A picture can be ignored, but when a mission's lifespan is suddenly cut short, it becomes a fact that can't be rewritten with words. At this very moment, the third center does something else that defies conventional logic. It doesn't simply exist, it seems to drag the wobble phase toward itself, and the entire equilibrium oscillation is reconfigured to accommodate it. Imagine a swing that's swinging steadily. You add a third point of support for a second, and the swing begins to swing along a different trajectory. Then the support disappears, but the swing has already begun to swing along a new pattern. This is exactly what happens to a node. Even when the window ends, the system doesn't return to zero. A residue remains, and the residue feels like memory. It's as if the space has remembered being touched and refuses to return to its former state. You want to know what the team does next, because just watching is no longer an option. They're starting to map not points, but boundaries. Where exactly the third center appears, along what line it cuts into the system. And the map begins to take shape. The emergence of the third center is tied to the geometry of the Earth-Moon line. Not to the calendar, not to the weather, not to the solar wind, to the geometry that coincides with the position of 3i Atlas. And this is where the story gets sticky, because a coincidence ceases to be a coincidence when it is repeated over and over again, with the same angle, with the same entry and exit times. Then they perform another test, as crude and honest as possible. They send a test radio packet during the window and measure the round-trip path with an accuracy of a fraction of a second. On a normal day, such a test would be boring. On this day, it becomes a disaster, because the packet returns not at one time, but at 2, as if the signal had traveled 2 routes. 2 roads mean 2 geometries. 2 geometries mean that the space between points isn't the same for seconds. It's as if it's split into variations, and the instruments see this directly in the delay. And here again, it's tempting to blame it on interference, but interference doesn't produce 2 stable delays. Interference produces muddiness. But here, the two lines are as clear as a ruler, and both appear in the same windows. After that, no one argues anymore that something is happening. They only argue about what exactly, because the word gravity is too heavy to throw into conversation unless you're prepared to explain every comma. They try to keep things simple. There are nodes where the balance is sensitive. There's an external factor that adds a small push. The push hits at the right moment, and the node behaves as if it had an extra support added. But if this is just a push, why does a third center appear, rather than simply a displacement? Why does the system offer a new location, rather than simply abandoning the old one? This is where phrases that usually don't leave the lab start to emerge, something like mode switching, not because someone pressed a button, but because the system overshot a threshold. A threshold is a simple idea. You can push a ball around in a bowl and it will roll. But if you tilt the bowl a little more, the ball will suddenly jump into the next trough. This is a different minimum, a different center. And that's exactly what the third center looks like. Like a new depression that appears for a few seconds, takes over part of the trajectory, and then disappears, leaving the system slightly more tilted than before. Now imagine that the devices at these nodes become not observers, but indicators. They are the first to sense the tilt, the first to pay with resources, the first to show that the map is no longer flat. In the next window, one device does something desperate, not because it's stupid, but because it's trying to save itself. It moves to a wider loop, further from the knot, to avoid getting caught in the fold. This reduces the risk of a failure to reach the third center, but it impacts communications. The antenna loses its ideal geometry, the communication window narrows, and the quality deteriorates. The team chooses to receive less data rather than risk losing the satellite. And this decision sounds like a defeat, even though it's rational on paper. Because when equilibrium points become a danger zone, you're forced for the first time to retreat from the places you built as a foundation. Meanwhile, someone notices another annoying detail. The third center doesn't appear in every window. It appears in every second or third, as if the system is testing different modes, and this seems like a setup. Tuning is a word you want to avoid because it's too human. But when you see the amplitude increase precisely when the devices have found a way to survive, it feels like an answer. It's as if the system isn't just making noise, it's applying just enough pressure to force the infrastructure to rebuild, and that's the most dangerous feeling in history. And then comes the moment that becomes a turning point for everyone inside. They try to predict the window where the third center will appear and launch a maneuver in advance to pass the peak on an already adjusted trajectory. The forecast is spot on. The third center appears, and it appears a little earlier than expected, just a few seconds, but enough to throw the entire plan off course. Previously, windows were like a schedule. Now the schedule has become alive, and this means that the next stage will not be about 3 centers. It will be about these centers beginning to move within the window. When the centers move within the window, you're no longer holding on to balance. You're clinging to a moving target in space, which itself changes shape as you fly there. And that's why the next part is worse, because in the next window, the third center doesn't completely disappear. It remains as a tail, faint but perceptible, like residual current in a wire. This tail does exactly one thing. It pulls the knot further than before, leaving behind a larger residue than all previous ones. This is the first time that memory becomes noticeable, not in micrometers, but in actual budget. The devices have one last trick. They can switch to an emergency holding mode, which is rougher, more expensive, but more stable. It's like walking on ice, not quickly, but with your feet wide apart. And in the next burst, one of the devices does just that. It survives. It holds on. But the price is a sharp jump in consumption, after which people no longer discuss if, but how much is left. And that's when someone asks the most difficult question, because it's logical. If the Earth-Moon nodes can be forced to operate in a new regime, can the same be done with other nodes in the system? Because it's not just the Moon that has nodes. Planets have nodes. The systems we use as roads have nodes. And if someone has learned to press on such places, it turns into a new type of spatial control. Right now, this sounds too far away and too scary, but the problem is, the first step is already here, in the most visible places, and it's visible in the fuel and signal delays. And then comes the final detail, which will leave even the most reassured observer speechless. A third center appears in one of the windows, and simultaneously a faint copy of 3 iAtlas appears in the long-range tracking images. Not a second object, not a tail, not an artifact, just a second spot where there was none before or after. It's as if the window not only changes the nodes, but for a few seconds changes how the object is visible at all. And if this is true, then the next impulse will not be about the devices losing their position. It will be about how the space between the Earth and the Moon begins to behave for seconds, like a device that can make copies of images. And then the question becomes both very simple and very difficult. If it can copy, what else can it do with those who are balanced? And that's when you begin to understand that a copy is more dangerous than any drift. Drifting wastes fuel. A copy wastes trust in your eyes and instruments, and without trust, space turns into a dark room. At first, everyone tries to hold on to the idle moment. The camera could have caught a glare. The algorithm could have gotten caught in the noise, but the window repeats, and along with it, the second spot repeats, like a trace on film. It's not flashy, it's not dramatic, it's just too neat to be trash and too well timed to be an accident. The strangest thing is that the copy always sits on one side of the main object as if it has a rule that cannot be broken. And when you superimpose the trajectory on the geometry, the rule looks uncomfortably familiar. The spot appears precisely when the Earth-Moon line passes through the window of influence. Not through coordinates, but through state. It's as if space changes not its form, but its properties for a second. And this property includes the second image. If this were a normal optical effect, different instruments would see different results. But here, it's worse. For some, it's a second spot. For others, it's a split in the signal delay. Different channels, one meaning. It's as if the system isn't just bending trajectories, but learning to work with waves, with how information flows from the object to you.
And at that moment, you catch yourself thinking that the nodes no longer look like places. They look like switches that can be used to change the transmission mode.
The first practical consequence isn't philosophical, it's practical and brutal. The team stops planning maneuvers toward windows and starts planning maneuvers around windows. It's as if you have a section of road in your schedule where the navigator is lying and you're not going around the pothole, but the fact that the map is unreliable there. But a detour costs more than a pothole. It eats up time, it eats up fuel, it eats up patience, and worst of all, it doesn't guarantee safety because the windows start to drag behind you.